Imagine Tesla publicly revealing a brand new Optimus hand patent, and then Elon Musk suddenly says, "That design is already old." Sounds strange, right? A patent is supposed to give us a glimpse into the future. But in this case, Tesla's future may have already moved on. The surprising part is that Tesla apparently tested a mechanism designed to make Optimus's fingers smoother, more precise, and more durable, only to discover that it simply wasn't reliable enough in the real world. And that tells us something fascinating about Tesla's humanoid robot program. Because the biggest challenge for Optimus may not be walking. It may not be balancing. It may not even be artificial intelligence. It could be something much smaller, the human hand. Today, we're breaking down what Elon Musk revealed, why this particular hand mechanism failed, why robotic hands are so incredibly difficult to engineer, and why abandoning a design might actually be a positive sign for the future of Optimus. The story began when details of a Tesla Optimus humanoid robot hand patent became public. At first glance, the patent looked like exactly the kind of technology people expect to see in a next-generation humanoid robot. One of the interesting ideas involved a rolling contact mechanism inside the finger joints. The basic goal was simple: create smoother movement while reducing friction and potentially improving precision and durability. On paper, it sounds like a smart engineering solution. But then Elon Musk made an unexpected revelation on Twitter. According to Musk, the technology described in that patent had already been abandoned. In other words, what many people were seeing as new technology was actually an older stage of Tesla's development process. And this is where things get really interesting. Patents don't necessarily represent the final product that a company is currently building. There can be a significant delay between filing a patent and the public actually seeing it. So when a patent becomes public, engineers may already be working on several newer generations of the technology. And that appears to be exactly what happened here. Tesla apparently tested the mechanism in the real world and discovered that it didn't provide the reliability needed for Optimus. That distinction is extremely important. A robot hand doesn't just need to move. It needs to move reliably, repeatedly, and precisely. Imagine asking Optimus to fold a t-shirt. It sounds easy. A human picks up the shirt, adjusts the fabric, changes grip pressure, folds one side, then the other. But for a robot, every single one of those movements involves a huge amount of coordination. The robot has to know where its fingers are. It has to understand how much pressure it's applying. It has to detect whether the fabric is slipping, and it has to constantly adjust its movements. Now replace that t-shirt with a fragile electronic component. Suddenly, the tolerance for error becomes incredibly small. That's why Tesla abandoning a promising mechanism isn't necessarily bad news. It could actually mean the company is testing aggressively enough to discover problems before the technology reaches customers. To understand why this is such a difficult engineering problem, let's talk about the human hand. The human hand looks simple: 5 fingers, a palm, a few joints. But underneath the skin, it's an incredibly sophisticated mechanical and biological system. The human hand contains 27 bones, along with tendons, ligaments, muscles, nerves, and sensory systems. And the really impressive part isn't any individual component. It's how everything works together. When you pick up a glass, your brain doesn't calculate every tiny movement mathematically. You simply reach out, touch the glass, feel its surface, estimate its weight, and automatically adjust your grip. You don't even have to think about it. For a humanoid robot, however, these capabilities need to be recreated using mechanical components, motors, sensors, electronics, and software. And that's incredibly difficult. Let's say Optimus needs to pick up an egg. Too little force, and the egg slips. Too much force, and the egg breaks. The difference between those two outcomes can be tiny. Now imagine doing that thousands of times. That's where reliability becomes the real challenge. Tesla's rolling contact mechanism was reportedly intended to improve movement characteristics inside the fingers. But real-world testing can expose problems that simulations simply don't reveal. Maybe a component experiences unexpected wear. Maybe the grip becomes unstable at certain angles. Maybe repeated movements create tiny mechanical inconsistencies. Or maybe the mechanism works beautifully during a controlled demonstration, but struggles after thousands or millions of cycles. And that's the difference between a prototype and a production-ready robot. A prototype only needs to work. A production robot needs to work again and again and again. If Optimus is eventually expected to operate inside factories, warehouses, restaurants, hospitals, or homes, Tesla can't accept a hand that works 95% of the time. Imagine your household robot successfully picking up your phone 9 times out of 10. That 10th failure could mean a cracked screen. Now imagine it handling expensive electronics inside a factory. The cost of failure becomes much higher. This is why robotic hands remain one of the biggest challenges in humanoid robotics. Walking is complicated. But manipulating the physical world with human-like dexterity is another level entirely. So what does this mean for the future of Tesla Optimus? First, it tells us that Tesla is not simply taking one design and pushing it straight toward mass production. Instead, the company appears to be going through rapid cycles of experimentation. Design something, build it, test it, find the weakness, throw it away, build something better, and repeat. That approach is extremely common in serious engineering, and it could become particularly important if Tesla really wants Optimus to operate at massive scale. Think about Tesla's automotive business. A car is made from thousands of components, but many of those components can operate within relatively predictable conditions. A humanoid robot is different. The robot is constantly interacting with an unpredictable world. A table might be wet, a shirt might be wrinkled, a box might be heavier than expected, a human might suddenly move their hand, a tool might be placed slightly differently. A robot hand needs to respond to all of these variations. That's why dexterity could become one of the defining technologies separating a useful humanoid robot from an impressive-looking demonstration. And there's another important implication. If Tesla is already abandoning designs before those designs even become widely known, then the technology being developed internally could be significantly ahead of what the public sees. That doesn't automatically mean the next Optimus hand will be revolutionary, but it does suggest that publicly available patents shouldn't always be interpreted as a blueprint for the exact robot Tesla is currently building. They may simply be snapshots of the development journey. And that's fascinating because Optimus is essentially a moving target. The moment we think we've figured out its architecture, Tesla could already be testing the next version. Now let's compare this approach with how people often imagine robotics development. A lot of people think building a humanoid robot is like designing a smartphone. You create a product, finalize the hardware, manufacture it, and then release the next generation a year or two later. But humanoid robotics is much more iterative. It's closer to developing an aircraft, an industrial machine, and an AI system all at the same time. The hardware has to evolve. The software has to evolve. The sensors have to evolve. The battery system has to evolve. And the AI controlling everything has to learn how to interact with the physical world. And Tesla's approach appears to be particularly aggressive. Instead of protecting every failed experiment from public discussion, Elon Musk openly acknowledged that this particular mechanism didn't make the cut. That's significant, because in technology, failure isn't necessarily the opposite of progress. Sometimes failure is the process of progress. Every mechanical design that gets tested and rejected provides information. Maybe the mechanism was too fragile. Maybe it was too expensive. Maybe it was difficult to manufacture. Maybe it didn't survive enough cycles. Whatever the specific weakness, the engineers now have information they didn't have before. And that information can influence the next generation. Think about it this way. If you are trying to find the fastest route through a maze, discovering a dead end isn't wasted effort. It tells you where not to go. Tesla's Optimus development may be working the same way. But there's also a warning here. Rapid iteration is powerful, but it doesn't guarantee success. Tesla still has to solve the much bigger challenge of turning impressive prototypes into reliable, affordable products. A robot that can perform a task once is impressive. A robot that can perform that task 10,000 times without a significant failure is commercially valuable. And a robot that can do hundreds of different tasks reliably is something entirely different. That's the real benchmark. So the biggest takeaway from Elon Musk's patent revelation isn't simply that Tesla abandoned a robotic finger mechanism. The bigger story is what that failure tells us about the development process behind Optimus. A patent that looked like a glimpse into Tesla's future may actually represent a chapter Tesla has already finished. And that means the real Optimus technology could be further along than the public patent record suggests. But there's a bigger lesson here. Humanoid robotics isn't just about making a robot look human. It's about reproducing the incredible flexibility, precision, strength, and sensitivity of the human body, especially the hand. And that is an enormous engineering challenge. The fact that Tesla tested a promising design, discovered its weaknesses, and moved on could actually be one of the more encouraging signs for Optimus, because the path to a truly useful humanoid robot probably won't be a straight line. It will be filled with prototypes that fail, mechanisms that don't survive testing, ideas that look brilliant in simulation but fail in the real world, and designs that become obsolete before the public even hears about them. The question now is simple. What does Tesla's next-generation Optimus hand look like? And more importantly, will Tesla eventually create a robotic hand capable of doing the everyday things that humans take for granted? Folding clothes, handling fragile objects, using tools, building electronics, and eventually, perhaps, helping people inside their own homes. That's the real Optimus challenge. If you found this breakdown interesting, make sure to like this video, share it with someone who's following the future of robotics, and let me know in the comments. Do you think Tesla can actually solve human-level robotic hand dexterity? And if you want more updates and deep dives on Tesla, Optimus, AI, and the future of technology, subscribe to the channel and turn on notifications, because the next time Tesla reveals something about Optimus, the technology we're seeing today might already be yesterday's news.